All right, let's get this thing started. So today we're going to be going over sort of how the automatic hole filling machinery that Isovector and I have been working on in HLS recently, how it actually works, and how you too can sort of use the library that we've developed to write something like this for really any language. So without further ado, let's just dive into it. So the basic idea here is that we wanted to have sort of a notion of type-directed metaprogramming. So what does that mean? The basic idea here is that given a type, so like I don't know, A, B, we want to synthesize a. Sorry, let me just get a better view of the screen chat. Yeah. If anyone has questions at any point, feel free to stop me. This is meant to provide resources to others, so hopefully they can use some of the work we've done. So yeah, if you have any questions, feel free to shout them out. But the basic idea here is, given a type, we want to be able to sort of synthesize a term of that type. And we sort of do that by breaking down types into sort of simpler sub-goals, right? So the basic idea here is we have like a tuple AB. We can synthesize a term of this type if we can synthesize an A and sort of synthesize a B. So with that in mind, let's sort of start with a very high-level approach of how to think about these things, and then we'll get down into the sort of the nitty-gritty of how the library functions and how you can use it. So sort of the mental picture I have in my head anytime I'm sort of thinking about this tactic stuff is that a tactic is basically some sort of black box with an input called a goal and an output. And we denote that as the extract, or ext. And this box can sort of create lots of sub-goals in the process of execution. And each one of these sub-goals itself will get resolved to a sort of extract. And we can do this lots of times. Goal and ext. So if this is the sort of tuple case, we can think about the goal being the A-B type, and this guy asks for an A, and this one asks for a B, right? Now the interesting thing is sort of abstractly, if we stare at this long enough, we realize that these compose really nicely, right? If we wanted to, say, wire up another tactic here, we can kind of just connect these goal extract wires. Up to another tactic. Which itself may have a bunch of goal, sub-goal pairs. Right? So if you think about this hard enough for a second, this looks monadic in a sense, right? We're kind of grafting these sort of solvers onto each other, sort of as we go down the tree. So that should be sort of the intuition here, is that we want this to be sort of a monadic style and think purely about the algebraic semantics of how this all functions, without even thinking about sort of the inner mechanics at all. We're going to focus entirely on the composition and then get to the mechanics of it later. So this is very much an example of the sort of algebra-driven design that is in vogue recently. And Sandy's talked about quite a bit. So with this idea in our head, we have to make a couple of quick distinctions here. There are sort of two classes of objects we need to consider. Two classes. The first one I'm calling a rule, and the second one I'm going to call a sort of tactic combinator. Or let me just denote this as a tactic. So a rule, we can sort of think of as the language-specific bits of any sort of tactic system. So if you're dealing with types, this is sort of how do I synthesize pairs? Or how do I synthesize function types? Or how do I synthesize inductive types? Things like that. And tactic combinators are sort of the language-independent parts. Exactly, axioms. So if you were to try and write a tactic system for, say, a type theory, you would basically open up the paper, look through all the judgment rules, and write them down. Or if you're doing natural deduction, you go open it up, look at all the deduction rules, and sort of write those down. So those are the primitives that we sort of compose together using the combinators. And segueing in nicely, a tactic combinator is something like try tactic A, and if that fails, try tactic B. Something like that. So we can think of this as sort of the algebra of gluing our primitives together. And that is entirely language independent. So we can write these sort of, in the same way that parser combinators are sort of independent of the thing you're parsing, things like many or some, it doesn't really matter what you're parsing at any point. We can sort of write those at a very, so what are tactics of combinators? I will get to that. There's sort of this subtle distinction here and here. There's a couple of levels we have to operate on, but for now, let's focus on sort of rules. I'll get more into tactics as we sort of start to expose more and more. So what sort of abstractly is a rule? Well, going back to our sort of drawing that we have before of the sort of box with the inputs and the outputs, a rule is a thing that can make requests for goals. That's terrible. Goal, and receive sort of responses for extracts. And based off the extract, it can make more requests for goals and responses for extracts. So we in the refinery library, we actually have a type called rule T. Let me switch to Emacs real quick. Getting ahead of myself here. So let's actually look at some of the HLS code that we have. HLS tactics. Yeah, so a rule would be something like if we have a binding and scope of type A and our goal is A. Yeah, sorry. I normally set the default font size before I start streaming, but I forgot today. So yeah, it'd be like, oh, okay, if we have sort of an A in scope already and our goal is A, we could use A. Or if our goal is a lambda, we just need to introduce all the things on the sort of left-hand side of the arrow into scope, and then produce a subgoal of the return type. So we represent those with this. Yeah, for sure. I'll probably upload this to YouTube as well. I've been really terrible about doing that in the past, but I want to get better about it. Refinery tactic. Okay. Yeah, so I'm gonna do something real quick. I set the default font size before I forget. 18. I think that's fine. May go with 20. Yep, that looks good. So yeah, there's this rule T type, which has an insane amount of type variables, and it's very scary at first. But the intuition here is really we just have sort of one function that we really care about here, the sub-goal function, which, so I'm going to use the term judgment, which we denote as the type JDJ, and goal sort of interchangeably depending on the context. I'm going to try and use judgment here more often, though. So we take a judgment, or a goal, and we'll produce some sort of extract, right? So if we sort of think how this would work for a tuple type, it would be like tuple, let's say, our is a pair type of A and B. We would have a tuple subgoal A and subgoal B. So yeah, the important function here is this subgoal thing. And it's monadic along the sort of extract. So as we get more and more extracts, we can keep chaining and chaining and chaining and sort of synthesize a term. So going back to our drawing, because the drawings are really the only way you can think about this in my mind, without going totally insane. We can kind of continuously ask, make requests for goals or judgments, and get extracts back. And at the end of the day, we will synthesize a term. So morally, we can kind of think about this as the type sort of JDJ to a list of JDJ, so the subgoals, along with a way of sort of synthesizing them all back together into a single term. So is everyone kind of with me so far on what we're kind of building on here? It feels kind of overwhelming at first, but really it's just, hey, I have a thing, I can break it down into lots of little sub-goals, and I can take all those answers to the sub-goals and sort of combine them together into one thing. That's it. That's all that's going on here. Now, the interesting thing is if we look at the implementation, we'll see that this is sort of, what is it? Just a new type over this proof state T thing. Yeah, this is very lensy and very perfunctory. It's actually just a version of pipes with a bunch of extra constructors. Version 1 was literally just pipes with a new type. But yeah, it's very perfunctory, and there's probably some cute lens stuff you can do with it. This is a perfunctor in like 20 million ways, and a monad in also 20 million ways. So yeah, this is monadic in this sort of A, which is an extract in this case. So let's think about this proof state T thing. But before we actually look at the code, let's draw some more pictures. So the whole idea behind proof state is that we want to capture this sort of bottom half of this drawing, of this sort of request response. I want a goal, you give me back an extract kind of deal. So that's on a different layer. Oops. So we do that sort of by the following. So we draw out a box like we had prior. Instead of sort of drawing the goals out, I'm going to draw them as dots for reasons that will make sense in a bit. And extract. And these are goals. These dots are goals. And these arrows back are extracts. So what if I had a function, sort of goal, and this whole block here is going to be denoted a proof state. Oh, and it's got an extract. going back. So we can think of this as sort of slicing off the, say, hey, I'm going to make a request for the initial request for the goal, and just a thing that has a bunch of sub-goals and what to do once we sort of solve the sub-goal, what happens next. And once we've sort of solved all those sub-goals, we're going to sort of synthesize them up into a single term. So if we had a function, goal to proof state, ext goal, and a proof state, ext goal, then I can form another proof state, ext goal. So if you squint at this long enough, or not even that long, you can kind of, and this sort of works by gluing along this function, goal to proof state, along these nodes here, and then wiring back the extract it produces into these wires, if that makes any sense. So if you look at this type signature, you can kind of see, hey, proof states form a monad. And that's a really nice algebraic semantics, right? We know how monads work. Monads have laws, so we can sort of, by realizing the fact that our sort of notion of proof state is monadic, we get a lot of stuff just sort of for free. So then the question becomes, how do we represent this sort of idea abstractly as code? And I'm going to sort of introduce this in steps because the actual type is gnarly. So the basic idea here is proof state ext jdj equal to. That's not valid Haskell. So we've got a sub-goal constructor. Yeah, I'm going to call this goal, just for clarity. And sort of a what to do next continuation. And then there's this sort of done constructor, right? So this, let me switch to Emacs. This type here sort of captures this notion that we had earlier of, I have a goal, and here's what we do once we solve the goal with an extract. And hey, I've solved all the goals now, here's the final extract. And this, again, is monadic along goal. And this idea right here sort of captures the essence of what we're trying to do. Granted, we're going to need a lot more sort of stuff and features as we go on, like, oh, what if this needs to happen in a monad? What if we need to carry along state? How do we, care about errors? But those are all pretty easy to solve, weirdly enough, once you accept initial encodings into your heart. Because that's sort of the theme of this library is, what if we initial encoded literally everything? What would happen? And we can kind of think about synthesizing terms, how that would work is we would just need a way of sort of creating holes. So if we had any sub-goal constructors at the end, we would just fill these extracts with holes and report an error saying, hey, you didn't solve this sub-goal. So without further ado, let's look at the actual type of proof state. So you can see the sub-goal constructor here, and we can see the axiom constructor here. But there's also like 300 different ones and 80 type variables. So let's go over each one of these sort of in detail. So we've separated out this sort of extract type into two extract types just because it sort of enables us to do rule a little bit nicer. but also prevents this from being invariant. You can think about this, most of the time these are the same type. We can throw errors, so if your tactic fails in any way, that's where this comes in. And that's just failure constructor. We have state. So if you need to sort of accumulate state along in a nice way that backtracks the way you want, you have to encode it into the type directly, so there's that. You can have an underlying monad M, so this is a monad transformer. And we're going to try and synthesize a goal here. So that's sort of it. And remember, this type here, all it does is sort of implement this diagram we've drawn here, and the sort of composition along these goal nodes. There's a bunch of really boring instances. Most notably, it is a monad along the goal type. So again, back to the diagram, it composes along the sub-goals. So when you do a bind, it takes one proof state and a function that produces a proof state and glues that onto every single one of the sub-goals. So composition is sort of like sequencing, but applying the second one to every single one of the sub-goals. So that's sort of proof state. Do I have any questions so far, or is everyone kind of holding on to what I've got so far? So again, rules, sort of the primitive building blocks. You have to write them sort of domain specific. Yeah, that's where a lot of the work comes in. Proof state is sort of the underlying abstraction behind rules and tactics that sort of composes really nicely, and we kind of build everything out of that. And on to tactics. So once you realize what's sort of going on here with this proof state, we can sort of create the initial drawing we had of a tactic in kind of a cheesy way, which I find very, very appealing. So this is sort of the drawing of a tactic that we had before. And the idea here is, well, to get this out of a proof state, we basically just need to add sort of a wire coming in here, wires going out there, and we can do that by just slapping state T on top of our proof state T. And that's literally what a tactic is. Like, not even like morally. That's literally what a tactic is we just throw state T on top of our proof state, and that kind of gets us the exact structure that we want. If we want to look at Emacs, that's literally it. We just smack a state T on there and just call it a day. And that gets us exactly the behavior we want. So that's sort of the basic idea of the internals of the library. Now let's use it to actually write some code. It's going to be a bit on the fly, but I think there's a couple options here. I'm kind of leaning towards doing like a very simple, like simply type lambda calculus sort of synthesizer, and showing off a couple of cute tricks you can do with this stuff. I suppose we should probably go over some of the basic APIs first, though. And just a reference, so if anyone wants to follow along, let me bring up the actual library. Drop it in the chat. So let's look at the sort of APIs here. As we can see, the tactics, they're sort of alternative in Monad Plus. So if you want to do like, hey, let's try one thing and then try another, you'd use the sort of alt spaceship. But that, it's a little subtle because you need like backtracking to kind of work nicely, which, say if you have one branch that will like kind of keep producing valid solutions, you need to, sort of nicely interleave things. So we have this sort of percent sign spaceship that does fare and are leaving. And that's kind of all we really need to know. There's a lot to go over here, so let's just start writing code. Okay, so first, let's write the world's worst lambda calculus. We've got variables. We've got lambdas. And we have applications. And we have types. Let's unit or tr. We can kind of add more interesting things on here later, but for now, let's keep it nice and simple. So let's see. First, we need to import tactic. No, I don't want to comment that out. So let's write our sort of first rule here, which I'm going to call intro. Well, actually, the easy one here is unit, which is going to be a tactic T. Let me look at the type for this. So our judgment type is going to be a judgment. Just for now, I'm going to be lazy. Is going to be a judgment string to type and a type. So we can sort of think about this as a context of variables bound to types, along with our double type. So if we want to be really fancy, and I think we do. So I'm in a fancy mood today. We can use a sort of type operator. Or not type operator, like a symbolic constructor to sort of get across the idea that this is an implication. So first one is going to be a tactic T. Our goal type is judgment. Our extract type is expr. Our error type is just going to be string. Prevent ourselves from writing this 10,000 times. Our state, we're not going to have any state for this. I don't think we're going to need a monad. You know, we might actually want the state, but whatever. We have a new type for that, I think. Okay. Non-scope tactic. Functor identity. I should add a type sim for this. Unit is a T of type. So we're going to use the rule function here because we're going to be introducing a sort of primitive rule here for how to actually synthesize things of type unit. For the lambda case. So if we've got, I don't think we killed out our hypotheses here, unit. Otherwise, we're going to throw error saying goal mismatch. We're going to import some stuff. Monad dot error. Because this sort of primitive rule is only supposed to work on sort of solving the unit goal. So we don't care if we're trying to solve something else, then don't want it. Um, so how do we solve unit? Well, that's easy. We just return a new thing on here, which I'm just going to call, I don't know, unit ty, and then unit pure unit. So this little thing here says, hey, if the goal type is the unit type, then we're just going to synthesize a unit, and that's it. You know, let's get fancy here. Pair ty, type, pair expert, pair. Get a little bit more fancy here. Rule, case, pair ty, ab, and throw error goal mismatch. So in this case, we're going to do pair sub goal A sub goal B. Couldn't match judgment. Oh. So I'm going to call this HYS for short for hypotheses. But we can just sort of think about what's in scope. And when we do lambdas, that'll make sense. So sort of as this has been the prototypical example I've been kind of talking about, if we need to synthesize something of the type, the pair type AB, we just need to synthesize an A and just synthesize a B. Yeah, it gets better. So if we have a lambda, A, B, yeah, there's some cute tricks you can do with this with sort of language design that get you quite far. So in this case, we are going to introduce a lambda constructor. We're going to need a way of sort of creating new names. So if our state is a string, I think this will work. Whatever. Do s name get, and then modify that name with I don't know, name. Even better idea. So our state is going to be int. So let's, yeah, name is just going to get, and then we're going to modify +1. And then we're going to do pure lambda show name. What is this? String graph. So this is the interesting part. So we're going to make a subgoal here, right? With get show. Subgoal. Is going to be happy. Why are you so upset with me on this day? Probably a precedence error. So let's see, body, subgoal, body. And in this case, we're going to have our name along with the type A added onto the hypotheses. And we're going to try and synthesize something of type B. Right? So we're just sort of extending our context with the new binding we generated, and then once we solve that, we've got the body of the lambda. So we're going to synthesize a lambda expression with the name in the as the argument. And lastly, we need one more sort of assumption. Actually, hypotheses, and goal. So what this one is going to do is we're going to, first of all, driving equal show and driving equal show. And we're going to want data.list because reasons. I mean, I should be using a map here, but I don't want to bring in containers because I'm lazy. Why can't you bring in? What? Oh. It helps if you put commas, yeah. So case find in hypotheses. What's this? Of just and nothing. So we're going to look for something of the type goal in the hypotheses. And how are we going to do that? Lambda x. There's that thing? Yeah, I was just sort of going over the basic shape of how things sort of glue together. The VOD should be up. It was basically just me drawing a lot of pictures. I'm sure you've seen a lot of these pictures before, though. ty is equal to goal. Yeah, I got a new haircut, I think last week. Feeling good, feeling light. Okay. So what do we need in this hole? Well, this is easy. We just write pure var x, right? Because, hey, we have sort of an x in our context of type that has our goal type. So if we sort of synthesize that, it means we just want a reference to the variable. Throw error, goal, mismatch. I'm lazy with these errors, and I shouldn't be, but who cares? This is example code. Why are you upset? Binding for goal shadows an existing binding. So let's do an example here. First, let's write a type. Yeah, no. That won't be annoying at all. I'll fix that later. Let's say we have a, let's add another thing, ty var. String, I don't know. So our goal type here is given a ty var x and a ty var of y. Let's make a pair type of ty var x, ty var y. Is that a valid type? Yep. Tempted to write some cheesy isString instances, but I don't think I'll do that. So let's see. What's this guy's type now? Tac. So let's sort of solve this the stupidest way possible, right? So we know we're going to do an intro, or a lamb. And once we do that, we're going to do another lamb. And then we're going to do a pair followed by an assumption. And if we run tactic, oh, and no, because those are just assumptions, right? We're using this assumption tactic to solve those. Yeah, we're just grabbing them from the context. Exactly. We might need this monad extract thing. Yes, there's another thing we're going to need. Poll. And we can't use identity here, so let's new type blah 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 poll extract a is equal to extract run extract a deriving. Let's get fancy. I'm in a deriving via mood. If I can remember the syntax for deriving via. Yeah, it's necessary, but I can't think of a nicer way around it. Deriving functor, monad or applicative. Via identity. This is the syntax for this. I can never remember the deriving via syntax. What's the fucking syntax for doing deriving via? Am I gonna just have to do this the annoying way? Yeah, that could work. Oh, no parents via. Okay. So it's just like this. Or, oh, do you have to write deriving? Oh, okay. Deriving functor applicative via identity. Cool. That's better than I thought it was going to be. So the basic problem here is that we need to there's this class monad extract. Expr extract. So we basically need to say, okay, well, say we sort of, in the progress of synthesis, we come across a goal and we don't solve it. So we're gonna need a way to have like a basically, hey, I didn't solve this this hole. I need to insert a hole into our term. And the monad extract sort of lets you do that. So if you're doing it like template Haskell, you're going to need to do this with sort of fresh name generation. So you're going to need to do it in a sort of monadic context. But if you have something like this, legal, multi-parameter type classes, wow, yay. So I think that's it. Run tactic T. So we run this against our judgment here. You know, let's run tactic, which takes a type and will return a sort of list of either strings or expressions and lists of judgments. Ty is equal to blah, 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 blah. t, so this is just going to be empty list. Y, the state is going to be 0, and I think that's... Why are you upset with me? Oh, we actually need to run a tactic. That's fair. Tactic comes first. Attack. And attack here. Very exciting. So what's this hole? Extract, so that's just going to be followed by a run extract. I hate triples. I should really get rid of this fucking triple. Whatever, we're going to put the state here because I'm lazy. Cool. So if we, for example, did something like run t with our tactic and our type, what can't I show? Driving each show or show. Left goal mismatch. Yes, that is going to be annoying. What did I screw up? Probably an associativity thing. Lambda. Yep. Yep, it's an associativity thing. I knew it. Lam, pair, and this is assumption. We can see that this actually synthesized the sort of term that we wanted, right? Lambda 0, lambda 1, pair 0, 1. With our no extra subgoals. So this is kind of interesting for a couple of reasons. For starters, we've basically written a sort of pseudo type checker in a sense, where I can write programs like this, and I'll get errors if I didn't do it right. So instead of having a type checker, we're basically saying, hey, the only way you can construct programs is via this correct by construction method, which is a whole very interesting idea, as it sort of opens the door to having type systems that are undecidable, like crazy stuff, like have the type of all programs that terminate, which if you're doing a sort of writing a type checker for, your type checker is undecidable, and that's no good. But for this, we can only do correct by construction programming, so we don't have to write a type checker, which is sort of interesting unto itself. And we can also do things like this. Auto, which is and auto will repeatedly try lambdas. Let's see, repeatedly try lambdas, and then we'll do choice of, let's see, what are things? Pair followed by auto, unit, or assumption. I think if I did this right, yep, there we go. Let's get the import data.either and get the rights. So this is, see, our auto tactic here, which is pretty brain dead, was able to synthesize this type without writing this sort of like, oh, we know what the type is, so let's sort of write out a tactic that we know will solve it. This kind of brain dead auto here is able to sort of synthesize things sort of regardless. Like if I just kept adding One sec. Infix R. Four days here. Just so I can get rid of these parentheses. Ty var z. Auto is going to still work. So if I even wanted something like pair ty here with a ty var x and ty var z, our auto still should be able to sort of solve it. So even with like minimal effort, we've got something that can synthesize sort of expressions in simply typed lambda calculus, with very, very little effort. Like this is 80 lines, and that's even to get the whole like lambda calculus in there. And we don't have a type checker, but all of our things sort of by fiat, because we basically encoded the typing rules for the simply typed lambda calculus's rules here. We got a type checker or a sort of program synthesizer for free. And obviously you can get much more sophisticated with this, like we've done with the HLS plugin. That's a lot smarter with its auto. Because we're, instead of just trying to do like, hey, let's get any old term, we're trying to find the best term, the one that you probably want. Yes, unit, pair, lam, and assumption are our rules. And choice is sort of these tactic combinators that I was talking about here. And tac and auto, yes, tac and auto are tactics. Exactly. The sort of tactic combinator is kind of an interesting distinction, but I use it for things that take in tactics as parameters and produce new tactics. So choice is an example, which will kind of run all of the tactics that you give it and produce a new tactic in doing so. And there's some other ones like commit, which will try and run T1, and if T1 doesn't succeed, it will run T2. Sort of interleave, which does the sort of alternative thing I was talking about. We have this like progress tactic, which says, hey, run this tactic, and if it doesn't do any work, fail. And the interesting thing is run tactic, if you look at its type, and we saw it here, is not only does it synthesize like one thing, it will synthesize all of the possible ones that it can. So if we had ty2, type ty2, ty var x, ty var x, to ty var x, it's interesting, I thought it would. Oh, yeah, okay. So we do need to get a little bit smarter here about using assumption in multiple places. Yeah, exactly. Change these. Okay, so for that one, you have to be a little smarter. This is where the state comes in. So you need to probably track usages in a state. Yeah. But it's not super complicated. And I think this approach is sort of really underexplored. Again, as an alternative to writing a type checker. Because you can kind of see how this is like a weird way of kind of writing programs. And if I wanted to, I could say lam x, make a version of this that sort of binds variables, and then have pair take in two tactics. And I could write a little weird DSL for actually writing programs using this. And I would not have to write a type checker, because everything is correct by construction. And this is sort of the PRL approach, or program refinement logic. So projects like New Perl and John Perl and Red Perl kind of use this idea of, hey, let's make our type system absolutely bonkers and undecidable. But who cares? Because we don't need to write a type checker. We just do everything correct by construction. And I do need to, I wrote my own version of these. I need to get back to it at some point. But it's a really fascinating idea. And the other interesting part is that Refinery is really useful for writing sort of program synthesis tools. But there are a lot of other problems that sort of fit the same kind of model of programming, where you have a thing, you can decompose it down into sub-goals, and if you can solve all the sub-goals, we can sort of perform a solution for the big thing. There might be some search. Like, I've been sort of toying with the idea of writing a sort of symbolic integrator or symbolic differentiator using this. Because it's the same thing, right? You have a bunch of approaches for like solving an integral, right? You can do like U substitution or like all these other fancy approaches. And there's not necessarily one best way to do it. You might want to kind of play around with it a bit. And this is sort of the algorithmic approach to playing around with something, right? We have a bunch of sort of things we can apply and transformations we can apply. Yeah, that's like, this should be perfect for that. I mean, as you can see, we basically have a weird version of the sequent calculus here and the lambda calculus. And this would totally blow it out of the water. I've also played, this was a long time ago, with sort of synthesizing English proofs, like proofs written in English from sort of symbolic goals, where you can, the basic idea was, it was for a number theory course, and there was a bunch of proofs where it was just like, they're pretty mechanical, but I need to sort of hop in the middle at some places. Yeah, I'm going to upload it to YouTube. So I definitely want this one to be around for a bit longer. But yeah, you can kind of write these little domain-specific tactics of like, trust me, and this is the proof. And have it sort of synthesize these long English proofs. Where it's like, oh, let us assume that, blah, 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 blah. And that was pretty cool, and it worked. And I actually submitted an assignment that I sort of synthesized all the proofs using this approach. The code, unfortunately, is lost to the sands of time and a dead hard drive, but there's a lot more to this idea than just synthesizing programs. It's really any sort of goal-directed programming that you can think of. This works extremely well. So does anyone have any sort of questions about sort of the broad approach, how this works, how you might be able to use it? And if not, I think I might just go on a bit of a documentation tear so we can kind of poke at all the corners of the library and get a really solid understanding of what they do. But for now, I'm just going to grab some water, actually. I'm out. Yeah, no problem. This was a really fun library to write. And just to plug the paper that this is all based on, it's the Algebraic Foundations of Proof Refinement is where I got a lot of these ideas from. Let me link it in the chat. It's a really fantastic paper. If you skip past all the sort of galaxy brain category theory stuff at the beginning, it's pretty readable. And all the core ideas are there, with the sort of key insight being that proof states form a monad. They do things a little bit differently for us for the sort of tactic combinators near the end, but I kind of like our approach a little bit better. Theirs is very semantically nice, but ours is a little bit nicer to program with, whereas they're doing pure category theory. But yeah, that's basically it. It's not super scary. It's, as you can see, pretty darn easy to use. So go out there and write proof synthesizers, everyone. I would love if someone added this to PureScript. Just as A, a proof of concept that like, hey, this thing actually works, and B, it would be really nice to just sort of be able to hit a button and say, hey, synthesize this gnarly type for me. What's the other one? Or even just this binding these little mini tactics like, hey, introduce a lambda to keys. or hey, do a case split. It's good for writing editor tooling or any sort of, yeah, I just want to decompose this thing down by like 1 or 2 steps. You don't need a giant full-blown auto because it's tricky. So if no one has any sort of further questions, I think we might just kind of goof around a little bit with documentation, or maybe try and write that symbolic integrator. I don't know. That could be kind of subtle, though. I'm not totally sure if I'm ready to do that on a Saturday without any thinking. At the very least, let's take a look at the README. It definitely needs some love. Example here. Refinery to synthesize. I'll do this later. It's not the most exciting content in the world. Yeah, let's try and write a symbolic integrator. Okay, so our expressions are going to be, so we've got literals in this lit, which is the, I don't know, double. Double's probably stupid, but who cares? We're going to have addition. We're going to have multiplication. And what are some other things that we might want to integrate? I don't know, sine, cosine, and that should be fine for now. So type T, A is going to be a same deal. This could be a bit embarrassing as it shows how much I've forgotten all my calculus. It's been a couple of years. Hopefully this will do it for me though. Tactic T. So this is going to, if we think about it for a second, the goals are going to be sort of synthesizing derivatives or antiderivatives for expressions. And the thing we are going to be synthesizing is also an expression. That's what a derivative is, right? Our errors are just going to be strings because we're lazy. The state is going to be unit, I think. What are we going to do for holes? I guess we could just adjoin a hole to this pretty pointlessly. Copy this. I am lazy. It's gonna load. Nope. I need to import identity. Okay. So let's bring up a new window, new browser window with sort of all the integral laws because I don't remember them, which is a little embarrassing. Basic rules of integration for calculus. Oh, the other thing we're going to need, now that I think about it, is this sort of notion of plus c for an integral, right? This could be a little bit tricky. Let's see. And let's do something a little bit cheesy. Instance num expert, where from integer, screw it, integer. From integer n is just going to be lit. Plus is going to be equal to the plus constructor. And times is going to be equal to times constructor. Why are you upset? Any parentheses. And no abs, signam, or negate. We'll add things on as we kind of work through this. I don't want to get too into the weeds here. So let's see. The rules of integration. What are they? Let me. Bring up a new tab. Sorry. Fiddling with the OBS is always fun. And transform. Where is that? Transform fit to screen. What is going on? Okay, interesting. I'm really bad at this whole streaming thing sometimes, I swear to God. Okay. And I need to be above that. Okay, so basic rules of integration. The integral of a dx is equal a to the x plus c. Okay, how is this going to work? Int a. T unit. Int a is equal to rule. So this is going to be a literal. Case lit n. Let's make a quick helper. Whatever. Dual mismatch. Why are you all upset? Okay. Oh, I forgot. For error, that means dollar sign. Swear to God, I'm good at writing Haskell. And I need to import 3,000 things. Okay, so if we got a literal n, the derivative of n is going to be x. Is going to be a times x plus c. Okay. Couldn't match integer with type expression. Okay. Is my cheesy num instance not going to work today? Blah, blah, blah. Oh, that's right, I need a pure. Yeah. There we go. And let's write our run t. I think we can kind of copy this. Expert. E and E. But so upset. So that's how we integrate a... Oh, crap. I just realized I wrote a bunch of code while not showing it. That's very, very silly of me. Good job, Reed. So yeah, this is how we integrate sort of a literal, right? Okay, let's look back at the our basic rules for integration. So if we have mul t lit mul rule case. So if we have a literal a times an e, then our resulting integration is going to be lit a times partially applied to subgoal e, and t and so that is how we integrate sort of multiplication of literals against expressions. Let's test this out real quick. Is equal to 2 times, oh, and lit x powers. Lit x is equal to rule case. So, or not lit x. This is just, I don't know. It's called x. It's a terrible name, but so if we have an x, then the resulting integral is going to be x squared divided by 2. So we need division. So this is an x squared. Well, I guess we don't need powers for these. Let's keep powers in. Divided by 2. Dx. Terrible name, but who cares? Example is an expression is going to be, I don't know, 2 times x. Auto, let's do this. Auto is just, so if it's going to be either a lit mul followed by auto dx. So let's do writes line t auto example. Does this look right? So it's 2 times x squared divided by 2. I think that's right. Let's ask Wolfram Alpha. This is a bit embarrassing, but integrate. Oh, I forgot a constant in there. No. Where do I need to add that constant? This is where Reed's pathetic knowledge of calculus from like 7 years ago is starting to fail him. Integrate 2x. Because I know it's 2x squared divided by 2 plus c. Which we're going to get this in a not simplified form, which is fine. But where does this plus c need to come in? I think it's not just integrating literals that I need to do the plus c on. I think I always need to add a plus c. Right? So let's how do I work that in? So I guess it's technically the integral of anything is equal to it's a times dx. Annoying. It's not an instance really isn't buying anything. Besides just being, I don't know, it is buying this stuff. Yeah. Think. Where does anyone have any insight into this? Of any cute ways of doing this? So I think that the plus c needs to come in every time we integrate anything. The cheesy one is do this. But I don't think this is quite right. That's good. Let's just ignore this plus c for now. We can get to that later. Okay, so if we're integrating a plus, then I think we integrate the two branches of the plus then. If that is what I recall. Yes. So if we're integrating a plus, rule case e plus or a f plus g. This is just going to be plus subgoal f subgoal g t plus. And let's throw a plus in here. So if we, 2x plus p times x. That's crazy, but it looks right to me. Cool. And of course, x more generally, when we have an exponential of sort of x to anything, any literal, then it's going to be x to the n plus 1 divided by n plus 1. Right? That's right. So then if we do something like this, uh-oh. Ah, that's right. We actually need to add that to our auto. Next, but doesn't have any subgoals. Use that. Exponential. Exponent. Oh my god, fucking freeway. Jesus Christ. That looks crazy, but it also looks right. So yeah, we have a really basic symbolic integrator here, which we kind of just wrote by kind of writing down the basic laws of integration and just kind of adding them in, which is cool because instead of having this big recursive thing where we need to consider all these cases, we can kind of just add along rules as we sort of like and just compose them together using like choice and recursion. I mean, we could keep going here with like use substitution and all that, but again, the basic idea is still the same. So just showing here that the programming model that this enables is not just about program synthesis. We can also do it for sort of other problem domains that are kind of goal driven. And let's add. Oh, we have sine, right? What's the integral of sine? It's look at our integration rules. What is the integral of sine? Alpha. It's Haskell from alpha. Integral of sine. It's pathetic that I don't know this, but it's negative cosine. Okay. This is going to be an overlap, isn't it? Plus sine. Sine is a rule case. So we've got a sine of E. It's going to be, for now, let's put a sine of X in there because I don't want to look up the whole rule. Then we're going to pure negate of cosine of X. And otherwise, sine. And I think cosine is similar. I think the integral of cosine is just sine, yeah. Cosine, cos, and sine. So yeah, you can kind of see how this might sort of form the basis of a nice little sort of computer algebra system that's really easy to write. It's kind of cute. I like it. I don't know, the integral of 4 times sine of X plus, I don't know, cosine of X. Yep, there we go. We got our integral. So, yeah, we can just kind of keep adding stuff. I don't know if I'm going to follow through on more of this, but this, yeah. I knew this would work, but I didn't think it would be this easy. Maybe we could try use substitution. Maybe let's just go for it. Get crazy here. Really wild. Okay, what is the rule for u substitution is, oh, we need to pick, there's the whole du versus dx thing. I don't know. I might need to get a little bit more sophisticated with my my expressions here. So I think I might wrap this little experiment up there, because I don't want to think about this too hard on stream, because thinking really hard on stream is not great content, because it's just lots of me staring off into the distance and mumbling to myself. But yeah, you could do something similar for derivatives or any other real, probably other sort of computer algebra problems where, you know, if we need to reduce this thing down, we need to sort of reduce the sub-expressions or any sort of cute stuff like that. That involves kind of goal-directed programming. So, yeah. That's kind of refinery in all of its glory. A surprisingly tiny library that does a surprising amount of things. Unless anyone has any sort of questions or anything that they would like to sort of see or things they would like answered, I think we might be wrapping this up soon in a little bit. Oh, one thing I forgot to mention is that sort of we've only been dealing with non-dependent subgoals and stuff like that. But this works just fine for dependent types out of the box. In fact, the paper I ripped a lot of this stuff from sort of had that in mind. So if you need to do things like existentials, this is super easy because our goals can kind of depend on the extracts of previous goals. So it handles sort of dependent subgoals just fine. In fact, it's super easy. Like if you look at simply type lambda calculus 1. I don't know. If we had some like crazy type here, like I don't know. So it's kind of hard, but like a dependent pair type here. I don't know. We might have to write a whole dependently typed language to be able to do this. I don't really know if I'm in the mood to write that. In fact, nah, I don't want to do it. But yeah, if we had a sort of a sigma type here, where it was like a pair, I don't know, like n type nat, and then some like predicate depending on the value of n. So let's say like a vector of length n of strings. Guys, we can still synthesize this because we'd synthesize the n, and then we would emit a subgoal for a vector of length n, where the end depends on the n depends on the thing we synthesized for this this half of the pair. And the same goes for like pi types. That one's actually not that hard because it's basically the same lamb rule we have down here. This is the only tricky one. So even doing like, one could imagine existential types for Haskell. We don't do this way in HLS, but we could, where we sort of synthesize a type and then present a sort of dependent subgoal based off of whatever type we synthesized. So this is extremely flexible in that regard. And you don't have to deal with like sort of crazy unification problems if you do things that way. It does present its own challenges because you need a way to sort of pick what type you're going to use. But it does extend quite nicely to the sort of dependent context. So, yeah. Does anyone have any sort of further questions, or is it about time to sort of wrap this thing up and keep it nice and short? Well, if not, I think I might cap this here. I'll be uploading this to YouTube for sort of posterity and hopefully be able to guide people to this if they want to use the library. But until later, I think I'm going to sign off for the day. Hope everyone has a nice, lovely Saturday, and see you all later.